Hello everyone, it's December the 7th. I'm getting more sick, but it's not too bad. It's not too bad. Just very, very stuffed nose. So I'll sound really weird. All right, I think we're bang on. Just keep doing easy ones, which I'm not complaining at all. Since they take a large um, worry off, right? It's always gonna be. Oh, I think I've done this before. No, 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 I have not done this before. Oh, people do not like this one. All right, let's go Java this thing. So what do we have? Um, Given the root of the binary tree, construct a string consisting of parentheses and integers from a binary tree with the pre-order traversal. Wait, what's pre-order? Pre-order is root left to right, right? Omit all the empty parentheses, pairs, and do not affect the one-to-one mapping relationship between the string and the original binary tree. Anyway, so if we want to go, so it's 1, and then 2, 4, right? 1, 2, 4, and then 1, 2. The hell is this? 1, 2, 4, and then yes, and then 3, and then left and right, and then there shouldn't be another one outside 1. No. So this is root 1, right? Once we're done, we have a parentheses. Now we have 2, right? And then we have a parentheses. Now we have 4, right? That's done because 4 is the leaf. And then we go back to 2, we have another parentheses, yes, because it's empty. And then we close it. Then we do 3. And the parentheses for 3, what is this parentheses? Exactly, what is this parentheses? Hold on. I think the difficult part is to figure out what exactly is asked for. All right, so my idea, so we do 1, right? So we have a parentheses. Because, oh, I think it's this, right? And then we do 2, right? And then we do 4. We don't have this. Now we go to 3. I mean, 3 is already the root, so we not root. 3 is already the leaf, so we don't need to have those, because you don't do it for 4. So why you didn't do it for 4? Why do you do it for 3? Right? So basically, we don't have this. So it'd be 1, 2, 4, 3. Is that right? 1, 2, 4, 3. All right, let's try this one. So again, 1. Okay, so we have 2. Left is empty, right is full, right? And then we go 3. So it'll be 1, 2, 4, 3. Huh? Oh, God. Oh, Lord. Oh yeah, you cannot do this. Omit all the empty parentheses pairs that do not affect, okay? Do not affect the one-to-one mapping, because the 4 can be on this side. I gotcha. So anything on the left side cannot be omitted. So, oh my God. So this is the answer. 1, 2, parentheses, 4, and then 3. Do you have another example? We don't have another example. Okay. All right, just how are you going to traverse it, right? And when they return a string, right? When they return a string, do we do string builder, or what do we do? I mean, anyway, so when we see the root, right? So we see the root, and if it's a leaf, we just return the string of the value, right? If it's a leaf, we just return the string of value. Otherwise, we will always create the value, right? And then we'll have the left. So we do tree to string. We say root dot left. And then because we visit this, and then we say right when you go to tree to string root dot right, right? And then it's the thing. If left is not empty, then we say, so we can say the rest is val, right? And then rest will equal to val plus this plus left. Oh, this it's basically, it doesn't matter what left is. If left is empty, we still have to add this. We still have to add the left because of this, right? But if it's on the right hand side, so is everything on the right hand side can be ignored. Yeah, if the right is empty, we can ignore it because we always the confusion happens if we have an empty on the left hand side. That's when the confusion will happen. Otherwise, we won't have confusion because it will be like this. We use parentheses to ward it off from everybody else. So we always do this, right? And then plus depends on the right. If the right is empty, we don't do it. If not, we just do right and this, and then return this. All right, let's give it a shot. I mean, I think the syntax will be more of a challenge for me. I want to do string builder is append, right? Maybe I don't do it append. Maybe I just, lazy. I mean, we can be lazy. Why can we not be lazy, right? So if root is equal to null, right? Default will be that. So we always return this. And then we can say string L is equal to tree this root dot left string. Hold on, let me sit more comfortably. Okay, string right is tree to this root dot right, right? And then we'll say if both are empty, then we just return myself. There's no parentheses. Yes, if L dot is empty, we can use this. And where's and? I'm trying not to look. Oh, come on. Oh, it's here. And right dot is empty, right? If that, then we'll return root dot val dot toString. Wait, why is it not right? Hold on, let me see. I have a definition. Val is int. How'd you turn? I never. Integer dot toString. Integer dot toString. Hold a second. VF this integer dot toString. There we go. Root dot val. Right. So that's that. If then we can return integer, right, dot toString root dot val plus left, okay, plus L plus right plus right dot is empty. Right, if it's empty, then we do nothing. Otherwise, we do left plus right plus this. Oh, I don't need integer 2. Okay, so I think that's what it means, right? We don't need to use this. Unnecessary. Okay, so without, we'll just do this. So it coerced, right? So we go 8k 0v. Let's try. Okay, looks good. Let's take. Oh, I've done this before. Good. It's better than last time. Last time I had a wrong answer. What was last time a wrong answer? I'm curious. What did I not? Ooh, what the hell was I doing? What? What in the world is that? Why do I have two things? Seriously, what the hell is this? What do I even use cube for? It's just DFS, right? Yeah, I think it's just DFS. This is not supposed to be here. I think it was wrong, right? I have no idea. No clue at all why I have this part. Because the Q does not appear again. Nah, I think it's something is wrong with this one. Yeah, let's check this one. I don't understand. There we go. That's the one. There we go. Yeah, that's the one. I don't know. I did it before and then it just weird. Looks weird. I don't know why people don't like this one. I think it's fine. I mean, people have their reasons. Maybe because it's old problem, right? So maybe when it first starts, it does not have a good test case. Usually that could be people's complaint. Like the test case, something is wrong or the problem was not well defined. But later on they changed it and it looks nice. It's totally possible. All right, so I have to check this one, see if I got it right. Sliding wind. Oh my goodness. We sort all the inputs based on time. Two pointers. Make a map to store the unique characters of the current. So yeah, it's the same as how I imagined. You have to sort both, right? You sort the first one. Yeah, you sort the second one, I think. Yeah, query, you sort both. And then you do where did you mp.size? Did you remove? You remove. I wonder, right? I wonder. Yeah, I'm equal to 1, right? Equal to 1. It will remove. It didn't do another one. It just plus 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 plus. Oh, you move this one first, and then you move this. Yeah, if it's equal to 1, because you're going to minus minus, so you just remove. What do you think? We think maybe we can try. Right, so we can try, just see if... no, that's not what we want. What we want is this. Yank. Alright, so what we're gonna do is we'll do this 3. Let's say, hold on. C2, what's the, oh. Let's try using len counter. Okay, so it'll be the same, counter is the same. I probably don't need this. We don't need this. Alright, so yeah, and then go up. Also, move high first. Right, move high first, such that we only need to check whether a server is still in the counter when moving low. Inspired by, better do this, I need to go to the front, because then E, and then we go right, do this. Okay, so this is all fine, this is fine, so we're gonna handle this one first. So we'll do this. Right, we do this. Oh, yeah. Right, so we go up here, we say handle the high. Oh, no, that's not what we want. P is what we want. We don't need this, okay? And this is just gonna be high. Yeah, all this is gonna be high. Right, so this is gonna be high, and then this is gonna be, we don't need this, okay? And this will be high, right? So high, just keep going. Right, handle the high first, and we do not need to check the counter. We just keep going, right? We just keep going. And oh, I think I did something wrong. Okay, let's go here. Yeah, this supposed to be up in here. Okay, yep. So handle high, we don't need this, then we don't need this. And this is gonna be low, right? And all this is gonna be low. This is low, right? And then this is a low. If it's equal, we don't do this. We say del counter logs low 0, and this is low plus equal 1. Then we do this is len counter. Let's see, this one works. It works. I don't think it's as fast as the other one. No. Oh, wait, hold a second. And I guess it is. Okay, let's try this. See if we get the same performance. Let's use this Oh, I have it. I have it open. So all of you plus this gigantic test case. Let's see. Huh. It might actually be faster. Because if the check on if is pretty slow. So we can avoid the check on if. And we use the delete is 01. And then we this. Maybe it is faster. That's the same. It's the same. No worry. That's okay. That is totally okay. All right. We'll call the end to this question. Move on. Oh, it's an easy one. Okay. Okay, easy one. We have to use Java. Number of beautiful pairs. You're given a zero-indexed integer array nums, a pair of indices I, j, where so I has to be in front of j is called beautiful if the first digit of nums I, the first digit of nums I, what? And the last digit of nums j are coprime. All right, coprime. GCD, right? GCD we check for coprime. Return the total number of beautiful pairs. What? That's it? 100, O squared, right? Not really. Oh, yeah, it tells you coprime in the GCD equal to 1. Well, because we only care about the first digit of nums I, right, and the last digit of nums j. Oh shoot, it's all single digit values. All right, so 2 5 that's 1, 2 1 that's 2, 5 1 that's 3, 5 4 that's 4, 1 4 that's 5. That's what is 5. Here 1 and 1, 1 and 2, that's 2. This will be 2 and 2. That's not coprime. So it's 2. Okay. So maybe there's a better way of doing this, right? There may be a better way of doing this. I mean, O squared definitely works. That's why it's an easy problem. Oh, Jesus, I already opened a new page. Okay. So we have nums, right? We have something, 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 and then something. So we can get the first digit out, okay? Okay, so we say, we'll call it A0, A1, A2, AN. And we get the last digit out, B0, B1, B2, all the way to Bn. So what we want to find is A0. How many of these are coprime with A0? Now, I am thinking of doing a counter, okay? That's how I'm thinking. Like, we can do a counter on this, right? So this will be a counter from 0, 1, 2, da 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 da. Ooh, what is 0? Oh, I was just going to say, what happened to 0? Okay, we have no zeros. All right, so we don't have zeros. So all the way to 9, so we have a count, right? We have a count 2, all the way to count 9. That's the last, okay? The last digit we have a count. Now we go from A0, okay? So we have A0, we know what A0 is, and then maybe we can create a map as well. Not really, yeah, it's, maybe it's faster just to go through everything. I don't know. What do you think? Which way will be faster? Do I do a list of lists? I mean, we'll define the list of lists, so I guess it's fine. right? So basically, we know like 1 is going to be 1, 2, 3 all the way to 9. 2 is going to be 1, 3, 5 all the way to 9. 3 is going to be 1, 2, 4, 5, 6, 7, 8. All right, and then 4. So we can create this. Nah, I don't think so. I don't think so. It's only 10 digits. This will be fast. So I'll just GCD them. So yeah, for every 1, I'll go through the whole thing, right? Actually, you cannot include B0. We will never use, right? This one we never use. So we create a counter for all of them, and we'll start from A0. We go through all of this. Whoever it is, we add the count, right? Once we're done, we remove this, so we take this out, and then we go to A1. Then we go through the whole thing. So by doing that, I can reduce the runtime to, we go n times, right? N times, and each one we go to 10 times. So 10n and times the GCD cost. And the GCD cost, I'll just call it 01, so we just don't consider. So 10n. We can try it actually. I'm actually curious. We can try both and see how much better the second one compared to the first one. That's actually interesting. Interesting investigation. All right, so we're gonna do, this is going to be the naive, right? Naive solution with O(n) squared. Very simple, okay? O(n) squared, very simple. What the hell did you do, man? O(n) squared. So we say, res is equal to 0, right? So for int I equal to 0, I smaller than num.length, I plus plus. Okay, and then for int j equal to I plus 1, we're going to say j is smaller than num.length, j plus plus, right? And then we say if math dot, I'm hoping there's GCD. Oh my god. You're kidding me, man. You're kidding me. Are you kidding me? Ugh. I remember I spent some time figuring out what Euclidean GCD is. Oh, shoot, I forgot. It's, Euclidean GCD is a way to factor, I think. Yeah, factor. I have this, talking about the GCD, not GCD. I have, something here. Wiener attack. Wiener attack. That's we need to use GCD. Rational to no convergence. That's not right. Arithmetic. Yes, EGCD. See that? EGCD. That's the one. They have to use EGCD. I'm just gonna copy and paste. Come on. There's no way I'm gonna write it myself. Oh, it's already done. No, that's fine. Let me think. I have to do this. Do shift to right. Okay. Right. GCD is if 1, but it has to be the smaller one, right? What if A is smaller than B? Yeah, so I remember if B is this, we return A, and then if A is smaller than B, If A is smaller, oh, I guess you don't have to. Yeah, I guess you don't have to. If A is smaller than B, then you put B as a bigger value, A mod big, then that will become the smaller value. Therefore, when, yeah, if A is smaller than B, you run it once, A become bigger than B. Yeah, it works. All right, so we don't have the GCD, which is really a shame. So we just call it GCD. Nums I, right, 0 minus 0, right, and then nums oh, holy crap, I need to get it first. How'd you get it first? Good question. How'd you get it first? How'd you get it first? Like, okay, get the last, you can mod. You mod 10, right? You mod 10, get the last. How'd you get it first? You can left shift. You divide by, can we not divide? You divide by 10 if it's 2-digit, right? You divide by 100 if it's 3-digit. But then you need to know how many digits there are. Oh my goodness. I absolutely don't like it. All right, I'm gonna cheat. I am going to not really cheat. I'm going to use string. So integer dot to string. So we'll do this. Okay. Then we dot char at 0 minus 0. So that's the front, right? The other one, the easy nums j, right? Mod 10. That's it. So if GCD is equal to 1, res plus plus, right? If it's not, this is not. So blah blah blah. Then we will return res. Okay, let's run this 6k 0. Okay. Blah blah blah. It will pass. Then we will move on to the second solution. Yep. Yeah, I think our, so this is the ON solution. We can still have this. We need a counter. Well, we don't really need a counter. We can't. We can have a counter because that could just be new int with 10, right? Because it is to 9, and then we say for int I1 actually, I smaller than nums.length I plus plus, say counter nums I mod 10 plus plus, right? That's your counter. And then we will do this one more time, but this is going to start from here. Then we say int f is equal to, so we go do this. We'll copy this p, right? So this is the first digit. Then we say for int, I like to k equal to 1. Okay, k smaller equal to 9, k plus plus, okay, k plus plus. If if GCD f and k equal to 1, rest plus equal to counter k. Okay, once we're done, counter nums I mod 10 minus minus. Actually not, it should be I plus 1, right? Yeah, DD4. No. DD, no, 4DD. Alright. Let's try this one more time. Let's see if this one right. Out of bound. Oh. Out of bound. It's very interesting. How would this be out of bound? Index 4 out of bounds for length 4. Length 4? The length is 10. Oh, you go to the end. It's nums. Ah, okay, minus 1. It can't go to the end. Yeah. Yep. There we go. It's Java. Okay? It's Java. It's definitely give you good runtime. Two, 4, 7, 8. Alrighty, that will be it. O(n) log m. Oh, okay, yeah, it's O(n) log n. I call it O(n). Oh, this is not pi. Jesus. Move LeetCode 2748 to LeetCode 2748.java. Okay. We want to do one more? How long have we been doing this? 38 minutes. Maybe? We'll just read through. If we can do it fast, then we just do it. If not, I'll call it a day. You are given two integers. We have nums1, nums2. In one operation, you can choose integer I in the range 0 to 60 and subtract 2 to the I plus num2 from num1. Return the integer denoting the minimal number of operations needed to make num1 equal to 0. If it is impossible, return minus 1. So you can choose integer I in the range 0 to 60. So num1 is 3. Nums2. Wait, hold. So we'll do 2 to the I. Okay, 2 to the I, and then plus num2. Then we'll do num1 minus this. And num2 can be, so num1 is a positive value. Num2, what the hell is this? What the hell is this? So 2 to the I, so I is 0 smaller equal to I smaller equal to 60. So we say num1, so minus 2 to the I plus num2, and then we are asking what is the minimal number of operations to make num1 equal to 0. Okay, we need to make num1 equal to 0. And num1 is 10 to the 9th. Sheesh. You got any ideas? I mean, this basically just one left shift, right? Oh lord, num2 can be negative. Well, let's say we take k times, right? Let's say we could take k times, and each time has to be the same, right? Each time has to be this. Oh dear me, each time is not the same, so I can be different. Ooh, maybe this is a representation. Maybe it's a binary representation problem, right? So basically, I can say I0. So I say num1. Yeah, basically num1 shall equal to 2 to the I0 plus num2 plus 2 to the I1 plus num2 plus da 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 2 to the I. Let's say we take k times, right? K plus num2, right? So it's equal to k times num2 plus 2 to the I0 plus 2 to the I1 plus da 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 2 to the I to the k. Right? If k is we just want to find the smallest k to make this possible. Okay. So if we find a k, so I'm actually thinking about binary search, right? If we find a k, then basically we say we'll do num1 minus k times num2. That's an integer equal to 2 to the I0, 2 to the I1, all the way to 2 to the IK. So basically the question is transformed to, given a k, can we make this happen, right? If we can make this happen, we try to make the k smaller. If we cannot, we make it bigger. Okay. And this has to be positive because these are larger than 0, which means we have the largest k. Or, I mean, in this case, we don't really have because num2 is a negative value. So k can be as big as we want, right? K can be as big. Is there a upper limit for k? Well, there gotta be an upper limit for k. There is upper limit for k. Upper limit, we can always find upper limit for k because I0, the largest, is 60, right? The lower limit is 0 possible. If k is 0, I don't think k can be 0 though. In one operation, you choose an I, and you have to subtract, right? So you have to do at least once. At least once. You cannot say 0 times has that do at least, unless, what if num1 is 0? Well, num1 is not 0. So you have to do at least once. So k, the smallest k is 1, right? So the largest k will be num1 minus k num2 equal to 2 to the 60 times k. So you can compute the largest k. Is that the largest k? Because you want k to be huge. Well, if num2 is a positive value, then we have a maximum k. If k is a negative value, right? If k is a negative value, then no, it should be 1, right? If this is a negative value, we want this k to be as big as possible, right? So k becomes really big, but its growth will not be matched by this. So we just do 2, otherwise we'll go too much. So we can use this kind of give you a higher bound on k. Is when this is very small, right? If it's very small, and then you do the most time. So yeah, we can calculate the Kmax, Kevin Magnuson, Kmag. Right, so we can do that. So we have this. Now the question is, how do we know, given a k, right? So given a k, we have this value. So we just want to know if it's possible to use k items to get to that value. Okay, so now the question is, we have 2 to the I0 plus 2 to the I1 plus 2 to the IK equal to a P, right? Which P is equal to nums1 minus K times nums2. Num2. Is this possible? How do we know? How do we know if it is possible? And I is from 0 to 60. Well, if P is odd, then it's not possible. If it's not possible, do we make k bigger or do we make k smaller? Oh, hold a second. This has to be even, right? This has to be even. So if num1 is even, num2 is even, then it will always be even. If num1 is odd, num2 is odd, k has to be even. Because k is odd, this one will be even, will be odd. Right? So if num1 is even, num2 is odd, k must be even. If num1 is even and num2 is odd, k must be even. So there are requirements on k. Yeah, but I don't think it follows. Like how does it even follow? Like, does it work? Like, how do we check if it works? It probably not even binary search. Yeah, example 2, because it's always going to be negative. So that's why example 2 is not possible. But always going to be an even number, but then we need to fit them together. So 2 to the k plus 2 to the something, plus 2 to the something. It's basically, 1 left, so basically the 1 plus 1 plus, 1. And plus, this plus. I always put 2 plus 4, right? Equals 6. So 2 is this, plus 4, no, 4 is this, equals 110, right? Yeah, the last must be 0. And then we can plus 4 again. We can 1010. It can be many. It can be anything. Oh, yeah. If it's 1 0 1 0, then it's 1 0 0 0 and 1 0. I see. I see. You deconstruct the binary. Oh, it's just the number of bits, right? It's just number of bits. So what we want to do is just try to see what is the minimum number of bits we can get. So in this case, so 3 minus k times minus 2, which basically is 3 times 2k, right? So we can say k equal to 1 is 5. 5 can be translated into 1, 1, 0. Can we now do like 2? This is not 5. 5 does not work because 5 is an odd number, so 5 doesn't work. Okay. And then next one, k equal to 2. Wait a second. How does this one work? Oh, we can do 0. My bad. You can do 0. 5 will work. So k equal to 1. So 5 is what? 1, 0, 1, 1, 0, 1. So this requires 2. Doesn't match, right? K equal to 2 is 7. 7 is 1, 1, 1, but equal to 3. Okay, k equal to 3. It'll be 9. 9 is, what's 9? 1, 0, 0, 1. Doesn't match. K equal to 4. 11. Wait. You just said this doesn't match. But they say a match. What? Because we do 4 plus 4 plus 1. Oh, Lord. Oh, Lord. Oh, Lord. Yeah, the first time k works. Well, if it immediately works, that's good. Otherwise, need to break it down. So 1, 0, 0, 1 can be broken down into 3. So we have a 1. And then 1, 0, 0, 0 can be broken down into 1, 0, 0 plus 1, 0, 0. Dude. How are we going to do this? Well, as the k grow bigger, but seriously, you're going to try every single k. And what else? Because it doesn't really follow. Like, if a k works, does that mean a smaller k? Yes, if a k works, try the smaller k. But if a smaller k doesn't work, it does not mean we have to try a bigger k. Maybe an even smaller k might work. That's the thing, right? You don't know. You have to go through the whole thing. Yep. To get a binary value, you try to see if we can just split it into. But 10 to the 9th, right? 10 to the 9th, it's definitely possible. Well, what we can do, right? We have a k. And we have the number. If we have more bits than what the k requires, like in this case, there's no way because the minimal number is this. But we have less bits, fewer bits, right? If we have fewer bits, then what we know is any bit can be broken into 2 bits. That's correct. Any bit can be broken into 2 bits. So depending on how many bits we have, right? So if we have one less bits, then we so can break 1 into 2, boom, then we get it. If we have 2, right, with 2 fewer bits, so let's say with 4, right, but we have, it can be like this. If it's 4 but we have this, right, we are missing 2 bits. Now if we're missing 2 bits, this one can break it into 2 bits, right? Each one that's not the last can be broken into 2 bits. So that's add 1. So if we have another one, we can add another one. But in this case, it's not going to work because we have this, so the extra will only have 1, which means each bit can double, right? Each bit can double. So we just count how many. Yeah, so the last bit doesn't count. So last bit will do. So now we have however many bits we need. We have however many bits we need, however many bits we have, and we try to see if we can match this. I think I'm almost there. I need to match this because each bit can split into 2 bits unless it's too huge, right? Unless it's too huge, but I don't think it will be too huge because 10 to the 9th is 30, right? It may be too huge. Yeah, so we have some, and we have what we supply, and then we just see each one can split to 2. So each one can count as 2, right? So if I have, let's say, 1100, this can basically, we have 2, but this basically can give me 4. Because this 100 can be 1010, this can be 100 and 100, right? Each one can become 2, so we can have 4. So we know we have the total number that's available multiplied by 2 is the largest possible. If they can match, if it's larger than this, then we have our solution, right? And then we just some don't get, right? Yeah, we can count like yeah, if it's a 4 and then we have 1, right? So we are short 3, right? We short, no, in this case with 3 and 1, right? 3 and 1, so we short 2. So we need 3, but we only have 1. So we multiply with maximum is 2, so it doesn't match. But if we have 2, maximum is 4, right? So we do match. And it doesn't really matter. We can have any value. As long as double it is larger than this, we'll always match. Because we can always double it up and then just remove. Yeah? As long as double it, match. Yes. So, what are we gonna do? Yeah, we start with num plus this time k. K will start with 1, right? And I think any number will work as long as this is larger or equal to 0, because I can always break it down, right? So we start with this. Each one, we find its binary representation, okay? We find its binary representation, and then we count how many ones there are, okay? How many ones there are. And then, as long as it's not larger than, it's fine, right? because maximum is 2 to the 60, right? And then if I have something is 60, right? Just 2 to the 60, so I can break it down into 30, right? But if I have it like 61, it's also fine. If I have 62, okay? 2 to the 62. So we need to break down and break down. So yeah, that's something we need to be more careful once it gets too big. Once the value gets too big. It might. Like if it's 10 to the 9th and a minus 10 to the 9th, it might. It might grow so big that this 2 to the 60 is 10 to the 18th. 10 to the 18th is 10 to the 9th plus 10 to the 9th. Actually, hold a second. Maybe it's not. But it is minus 10 to the 9th, right? And divided by 10 to the 9th. So our k is like 10 to the what? K is 10 to the 9th. I don't think so. So I think we don't have to worry. We just, k start from 1. We compute num1 minus num2 times k. Get its binary version. Remove, if the last one is 1, we remove it. And for the remaining, we do double it. If double it is larger or equal to, no, I'm gonna do it one more time. We do num1 plus k minus k times num2. Okay, so k from 1 all the way go up. We get a value. We get a binary version of the value. And then we count the number of bits in it. And then if the last bit is a 1, so we have to discount it. And also discount from 1. And if the total bits is larger than k, it's not possible, because that's already the minimal. But if it's smaller, then we check if double it will work. Okay, I think I can code it, but I choose not to because it's already 1 hour. I'm a little bit tired. So let's just call it a day. So tomorrow I can code it up and see if it works. All right, I'll see you guys tomorrow. Adios.